Hello everyone. In this episode, we'll go over transformers positional embedding. So along with attention algorithm, one of the key idea in transformer is to positional encoding, which is to trace back the relative position in a sentence where the word belongs and how distant it is with other words. Uh, and there's a clever algorithm for that. So I guess it's where each word sits in a sentence. Without it, the dog bit the man and the man bit the dog is like identical because transformers process all the words in parallel and no built-in sense of order. Okay. So the big picture is that we saw self-attention and how it computes the compatibility scores between word pairs. Uh, but the attention treats like as a set, like not in a sequence in that the orders doesn't matter. Okay. So positional encoding fixes this by adding the um, position dependent vector in each word's embedding before it's entering the attention layer. So the transformer paper, there was a famous paper by this, uses the sine and cosine waves in different frequencies. Um, and it's actually not like a random idea that popped out. It actually has been long time in mathematics for motor designers and electric motors to trace the rotational position um, um, using this idea. Okay, so and transformer, the engineers basically borrowed this idea from there. Okay, so okay. So the goal is build positional encoding from scratch and visualize it and understand why the sine and cosine waves are the right tools for the job. I'll show you why the order matters, why simple approaches like just tagging the integers, like the first word is now on one, second one is two, sort of things will not be ideal. And the sine and cosine positional encoding is how it works. And clock or motor resolver analogy and compute visualize this positional encoding for the real sentence and then the rotation matrix property to show you how it works and add the p toward embeddings and see how it looks like. And here are some references like again the original article for this here and also some illustrative example here. We changed the numbers a bit, but this is sort of inspired by this article. So let's set up Google Colab. So the first thing is the word order matters. Like the dog bit the man and the man bit the dog is like different, isn't it? And without the position, you cannot really distinguish this. Um, so the like LSTM kind of recurrent network gets order for free because it processes words one at a time from left to right. But the transformer protocol processes all words in parallel and then makes transformers fast, but you'll then have to somehow encode the position. So that's the idea. So why some approaches fail? So add the number position directly, like add 0 to the first number embedding, 1 to the second, blah, blah, blah. And if you have a long sentence like 99, then if you add that to the embedding, which is typically between -1 and 1, then this embedding is completely overwhelmed, isn't it? Also normalizing by sentence lengths, like fractions, like the position 0 gets 0 divided by n, like, and all this. Then, well, the same position in different lengths sentence gets different values, and that gets also not ideal. All right. Okay, so what do we do? So eventually, for a long time, people have been using to position encoding position the following. So the transformer uses like the sine and cosine functions, like the positional encoding. So here's for particular position, and one uses the sine wave, other one uses the cosine wave of this kind of some space frequency. The position of the word index is like the dimension pair 0, 1, 2, 3, or something like this. And then the D is the total dimension of the embedding. Okay, and they use 512 in the original paper. And 10,000 is a constant that controls how quickly frequencies decrease. Okay, so reading this formula, dimension come in sine and cosine pairs. So dimension 0 uses sine, in dimension 1 uses cosine at the same frequency. Dimension 2 uses sine at lower frequency, and dimension 3 uses cosine at the lower frequency, and so forth. And as I increases, the denominator 10,000 to the power of 2i over d gets larger, and the wave oscillates more slowly, right? And early dimensions change rapidly across positions like high frequency, and later dimensions change slowly, like a low frequency. So this is sort of like a basic trigonometry. Why values always are between -1 and 1, because the sine and cosines always output -1 and 1 in between the value. And P never overwhelms the word embedding, which are also in between -1 and 1. So why encoding is independent of the sentence length? Because the formula depends only on position I and D, and the sentence length does not really appear in position 2, always gets the same encoding and solving the problem. So here's to implement the positional encoding. For example, here's a maximum position and the dimension of the model, um, and see how it works like. So it basically sine and cosine, cosine, sine. So the first position 0 will get always this, okay, like 0, 1. So sine 0 is 0, cosine 0 is 1, and like this, and even in higher or lower frequency, but the next word will basically start changing like this. Right? So the motor or clock analogy. So first the motor analogy. So in electrical engineering, a rotary resolver measures the angular position, where in which angle it is the motor shaft, and it's kind of important for motor controls. It outputs two signals, sine and cosine theta at the shaft angle. And why is this two angle? Because sine alone is ambiguous. Like sine 30 degrees and sine 150 degrees, both gets like zero point 0.5. And I don't know whether it's 30 degree or it made actually 150 degree. That's confusing. But if I add the cosine 30 degree, then cosine 30 is 0.7, cosine 150 is minus 0.87. So now with the sine and cosine paired together, I know actually whether it is 30 degree or 150 degrees, isn't it? So that is kind of the clever idea. And in the clock analogy, why do we use different frequencies? Well, it's like the um, in the clock, a minute hand and second hand and hour hand. Like the second hand is a very high frequency. It makes revolution every 60 seconds. It tells me very fine-grained high frequency time within the minute. And then the minute hand is turns every 60 minutes, tells me a course of time within an hour, and then the hour hand completes the revolution in every 12 hours. So if I only had the second hand, I cannot distinguish, of course, between 1 o'clock, 0 minute, 30 seconds from the 2 o'clock, 0 minute, 30 seconds. But with three hands together, of course, I can pin it down. Okay, so the positional encoding takes several dimensions at different frequency, I mean, at different speed. Um, and the angle is measured by the sines and cosine pairs always, isn't it? So that gives me a unique fingerprint, basically. So the second hand, minute hand, and hour hand basically pins down the position for me. So now the positional encoding for the apple is red. Okay, so how does it work? So we use like a dimension 8 here, and we have four pairs of sine and cosines to visualize. Okay, so let's see. So position 0, it's sine 0 is 0, cosine 0 is 1, and even at higher frequency, it's the case. But then the apple, again, already also turns the sine 1 over divided by 8 and all this, like you can do the calculation. And so the positions are all uniquely kind of having a different vector, isn't it? Uh, and visualizing the full P matrix as a heat map, if we have dimension of 64 and maximum position of 50, you can see that, and none of them are actually it's the same. So you can actually see the correlations, and the nearby ones are having higher correlation, but you can see that none of them are kind of identical. And so why we use the sine and cosines and nothing else? And the main reason is because all this neural network and it relies on matrix algebra, isn't it? The weight matrix and all this. And the sine and cosine actually pair has an interesting property, like the shifting property, that if there's a particular position and we shift it by an angle delta, then, well, the trigonometry formula from high school will tell you this is kind of how to spell it out. But more conveniently, we remember this in a matrix form, meaning that the shift in sine cosine pair shifted by some difference delta is actually having the sine and cosine and multiply this matrix. And whatever the p is, it doesn't matter. If it shifts it by delta, then just multiply this, which makes it really convenient to embed in any matrix operation, isn't it? If you use the integer instead, then you actually have to have multiply the position, let's say position 5 bit 2, which will be 10, and it just doesn't get intuitively simple. So anyway, so here is basically some of the rotation where you can basically manually compute um, with this rotation matrix all by hand. Um, and visualizing the rotation here, so with a couple of positions here, basically can show you position 1, position 7, 0, 6, and so forth. So I can see easily position 2 here and position 5 here, how distant they are. All right. So now this apple is red. If I have the positional encoding with this particular embedding and it's added, so this is how it looks like. Or so the embedding and the embedding brush positional encoding looks like this. So now you can see that we can have a meaningful embedding. Right? So this is sort of basically going over the basic idea of how positional encoding works so that we can have with sine and cosine pairs basically simply just record the relative position of a word in a sentence. Okay. Thank you for watching this episode.